Hi. My name is Alex Bennée. I'm here to talk about the validation work we did on the QEMU TCG for the ARM v8. So ARM v8 is an interesting new architecture from ARM. It doesn't just add more bits, it's basically an entirely new instruction set. Last year, Linaro was asked to expedite support for the new architecture into QEMU. At that point, ARM v8 hardware was pretty scarce, and the only solution for those that didn't have access to pre-production silicon was to use ARM's foundation model. So as a result, there was quite a strong demand for a QEMU-based emulation that free software hackers could use to develop and enable their ARM v8 software. So the introduction of a completely new CPU architecture provides quite an interesting engineering challenge. A large chunk of the implementation would be brand new code, and we all like to think that we write bug-free code, but how do we ensure that we introduce this code and don't spend a long tail of the time fixing all the bugs that we introduced? So let's look at the estimates of how many bugs we could have put in. According to Coverity, a project around the size of QEMU can expect a fairly low defect rate of about 0.65 defects per 1,000 lines of code. This estimate assumes that because we've got a large number of talented open source hackers doing peer review on the mailing lists, that we keep our bug rate low. This is probably a little optimistic for the TCG code base because it's a fairly specialized piece of code. I did an estimate based on the defect rate looking at the ARM v7 translator. I looked through the commit logs and I counted any commit that mentioned the word fix, and that found me about 100 credible TCG fixes that had gone into about 9,500 lines of code. So that gives us an upper bounds of about 10.96 errors per 1,000 lines of code. So let's look at what that means for the code base. So I picked some of the most popular TCG front ends, and that's around about 60,000 lines of code. As you can see, given the defect rates, that's quite a wide range of bugs, but even the most optimistic estimate still predicts that we'd have about 40 bugs in that 60,000 lines of code. In the end, the AArch64 implementation introduced about 17,000 lines of new code. So given those defect rates, we could probably expect to introduce between 11 and 185 bugs. Now, obviously, we're not going to be doing this in a vacuum. We're expecting to do some testing. So let's look at what the old standby test of a kernel boot will actually test. So this is the standard. This is an AArch64 kernel with a basic 64-bit user space on the current QEMU master branch. I've excluded all the KVM files and also all the GDB files, which aren't going to be exercised by it. As you can see, we have very good coverage of our QEMU boilerplate code at the top there. As you go down, you can look at the CPU files, and you can see the coverage is already starting to drop off. Looking for green and red. So as we go down, it's all defined. And you'll see there's whole areas that we don't test, but mainly this is because there's functions for different ARM variants which we're not testing in this case. Then we get down to the first really big file. So this is translate A64. So this is the main dispatcher for the AArch64 translation. And as you can see, the coverage is not really good at all. Depending on how you count it, you're covering about 30% of the code base. Oh, you see all those big chunks of red.
What's the difference between green and red?
So red is not covered, green is covered. If you see on the green sections, these numbers here is the number of times it's been across these lines. So as you go further down the graph of coverage, you see it drops off quite quickly. As you might expect, the kernel doesn't really exercise any of the floating point or any of the vector instructions. So if we take a sort of conservative estimate of 30% coverage, we'll probably catch a few of the bugs, and that will only leave us with between 9 and 160 bugs left in the code that we've just written. So clearly we need to do something a bit better. So this is Risu. It stands for Random Instruction Sequence in User Space. It also happens to be the Japanese word for squirrel. So Risu is a program that executes a sequence of instructions. There are always two Risus. There is a master and an apprentice. The apprentice runs on the platform being tested, and the master runs on your known good reference platform. They communicate with each other over a network connection, and when their behavior diverges, the test is considered a failure. So let's have a quick look at the test sequence. So a test sequence is basically a raw binary. It contains position-independent machine code, and it's directly mapped into memory by Risu and executed. So if we have a look at the contents of the test sequence, we can see there's a couple of things in it. So first of all, there's a bunch of setup code. So this is just basic code that initializes registers with random values. It also sets up a block of memory that contains random data for our load store operations. Then we have our test instructions. These are generated from a template, which I'll talk about later. And these are the things that we're actually testing to exercise our translator. In some cases, the individual instructions will be wrapped with a couple of helper instructions around them, just to ensure that we're using the same values. For example, when we're doing loads and stores, we don't want to do it into random memory. And finally, we have these pseudo-Risu operations. So this is the principal mechanism by which the two Risu processes communicate with each other and synchronize their checks. So what are the Risu operations? So these are architecture-specific reserved opcodes. So basically, when they're running, they trigger an illegal instruction exception on the host, and that exception is caught by Risu's signal handler, and then the operation is extracted from some additional bits in the unused bits of the instruction field. So there's a couple of common operations. The most common operation is to compare the register sets between the two processes. We also have a similar operation for comparing the contents of the memory block. And then there's a couple of helper functions we have. Get set memory pointers, so we can set the address of the memory block that we're going to be using. And finally, there's one that indicates we've reached the end of the test sequence. So let's have a look at a typical execution sequence. So this diagram shows the typical execution flow when we're running a Risu-based test. Once the main binary has been loaded and sets up its communication with its partner, it sets a signal handler to catch the illegal instruction exceptions, and it basically just long jumps straight into the code. So it depends on how familiar you are with the ARM code, but at the start we've got a bunch of initialization code, so we're just making sure that the flags are all reset to reasonable values. We fill in random values into all the registers and also into the floating point registers. And we set up a block of random data that we're going to do our loads and stores into. After that, it will just start executing the randomly generated instruction patterns. So as you go down here, the first mobkx30, so that's on line 36C, that's a randomly generated instruction. The next thing happens is a Risu operation, triggers an illegal instruction. It syncs the register state between the master and the apprentice, advances the PC, does a sig return, continues. Now, obviously, add is a fairly simple instruction to test. When you're doing load stores, as I've mentioned before, we've got a few extra instructions wrapped around to make sure that the address we're testing is something sane. So here you can see the example of generation of the test pattern. When it comes to instruction testing, it's important that we test as wide a range of the encodings for the instruction as possible. You might, for example, have a bug where your translator fails if the destination register field is using the most significant bit, and you may never know about this until your code comes across some particular register-heavy code. So the range of the generated instructions is controlled by this template. Don't worry too much about the details, but you can see there are a number of fields. So obviously we have fields for the source and destination registers, but there's also 3 bits for an option field, 3 bits for an immediate field, and the SF field, and these all change the way that the instruction behaves. Now the template allows us to specify the size of all these fields, And then the generator basically picks random numbers for each of those fields and generates the instruction. We have an additional constraint here. So this constraint says the instruction is not valid if the Rn is not 31 and Rd is not 31 and the immediate value is above 4. And in that case, it just throws the instruction away and tries again. In this case, about the only thing we're doing is we're trying to avoid the ADX manipulating the stat pointer because we're going to be taking signals. We don't want to mess around with that too much. For convenience, the additional encoding we've got down here, ADX res, is just a way of us testing all the reserved encodings for ADX and making sure that they all behave as well. So let's look at a slightly more complex example. I mean, this is a load-store test pattern. The template's pretty much as before, but we've also added an additional constraint from memory, and this is making sure that the memory pointer that we're going to use is correctly aligned for the instruction, and also a calculation so the generator can make sure that the address we're using points at the right place. It's probably easier to see this in the generated code. So here you can see some example generated code. First thing we've got is we've got generated a random offset, and we execute this Risu operation get mem block. So that will return a pointer into our memory block with the appropriate offset added. So that's a properly aligned offset. Then the generator has spat out some code, lines 3 and 4, to make sure that the random values that we're going to use in the register and the index, once they're added together and used in the load, will actually point into our memory block. Otherwise, we're just going to segfault straight away. So we do the load instruction. We recalculate the offset. So if the memory block moves around, the compare that we're going to be doing is the same between the master and the apprentice. And then finally, the two Risu operations at the bottom compare the memory block and compare the register set. So Risu is very much focused on testing normal user space instructions. So it assumes all the interesting things that have happened have occurred either in the general registers or in a specific block of memory. So the generator currently doesn't, so you can't currently do anything like system instructions or stuff like that. Also, it's not able to do any branch instructions because these mess around with the program counter, which makes things a little bit more complex for recovering from a signal. We could probably work around that, but at the moment it doesn't. And then finally, we avoid manipulating the stat pointer, as I mentioned before, because we're going to be trapping signals and we don't want the stack to be broken. So let's talk a little bit about porting. Risu was originally written to support the debugging of the ARM v7 architecture. However, adding a new architecture isn't overly complex. Aside from all the instruction templates, which are fairly tedious, it took us a couple of man-weeks to add support for AArch64. I think it's perfectly reasonable for a new architecture to have something up and running within a fortnight. I'll just quickly run through the main porting activities. So, Risu itself is written in C. The code has mainly got boilerplate code for dealing with usual architecture-specific CISMs. So we're talking about things like reading register values out of the SIG context, advancing the PC, reporting the contents of the registers to standard out. For the AArch64 implementation, it was about 300 lines of C code, so it's not a lot. About the only thing that's potentially tricky is deciding if you want to mask some of the values. So it might be that in your register SIG context, there's values that aren't directly related to the execution of the instruction you're testing. One thing we do, for example, on AArch64 is we put a fixed value into the stack pointer before we do the register compare, because the stack on the master and the apprentice might be in different places because of address-based randomization. Then there's the code generator. Risu GenScript is written in fairly clean Perl, so it currently only has to deal with ARM architectures, but there's a reasonable separation between the target-specific and generic code generation code. The sort of areas you're going to need to address, you'll need to be able to generate a block that initializes the registers, values, and the memory blocks. You'll also need to ensure that there's support for all your various load store addressing modes that do the appropriate manipulations on the registers to make sure you're pointing at same memory values. And finally, you need to find somewhere in the opcode space that will generate an invalid instruction that you can use for encoding your Risu operations. So about the largest amount of time you're going to spend is going to be on the instruction template. If you're lucky, and we weren't, you might have machine-readable definition of your instruction space, and that would be great. Otherwise, hope that your PDF cut and paste well, so you can cut and paste the bit patterns into a text file and build the template definitions. But the only piece of advice I would offer is don't go too deep into specifying each individual instruction type. If they're all in an instruction group, just specify the instruction group and let the Risu code generation do its thing. So with that introduction to Risu, I'll just talk a little bit about the AArch64 implementation. So Alexander Graf and Michael Matz from SUSE had already posted some RFC patches for AArch64 to the QEMU mailing list. They were using them to support SUSE's build farm activities, and the patch set had grown organically to basically address this use case. And even Alex, I think, acknowledged it had some bugs in it. However, having a broadly working user space emulation would be very useful for us for our next steps. So after discussing with Alexander and my colleagues at a Connect conference, we decided that while it was useful having the SUSE tree, we were going to start with a completely clean slate. Part of that motivation was that we wanted the decoder to follow the ARM architecture reference manual, so there was a nice mapping between the actual documentation and the decoder. So once we had our skeleton file, we were able to take the individual instruction implementations, sometimes using the SUSE tree as a reference, address any outstanding review comments, and rebootstrap Linux user. And once we got to that state, we were able to run Risu, and then we could start testing. So once we had enough work, enough to have the Risu binary working, we started testing those particular instructions, and then we divided the remainder between the three of us. So that's Peter Madel, Claudia Fontana, and myself. We split the remaining groups between us, did the implementations, sometimes using the SUSE tree for reference, but every time we always tested our patterns using the Risu tool. So the timeline for this work, we first talked about it at Linaro Connect at the end of September last year. During that week, we managed to get a hacked-up prototype of Risu running on the SUSE tree, and in fact, it already demonstrated it was able to find bugs. After deciding what our approach would be, I went back to my old job and had to serve out a 3-month notice period, which was rather tedious, and Peter and Claudio got on with doing the initial bootstrap code. So I joined Peter and Claudio back in November, where they'd been working away getting the bootstrap work done. We had a fairly intensive development period as we rushed to get Linux user support in by the soft freeze deadline. A fairly bit of a baptism of fire for starting a new job. But by April, for the QEMU 2.0 release, there was a complete Linux user implementation for AArch64, except in crypto, which is an optional extension. By August, we had system emulation up and running, and someone had kindly also done the crypto instructions. So with all this extra testing, shall we see what our coverage looks like? So let's just remind ourselves this is a standard kernel boot, and let's compare it with what we actually achieved. So this shows the result of us running our current Risu-based continuous integration test loop on system emulation. Now you can see that translate A64, the main dispatcher, which was about 30% before, has now jumped up to about 80% coverage. There are a couple of gaps in here, so mainly they include debug code, things like non-standard exceptions that aren't normally triggered by the normal kernel boot, so things like hypervisor and GDB debug exceptions, that sort of thing. Some of the less used branch opcodes, and this coverage also doesn't include the crypto instructions. The crypto instructions were a bit of a pain because the foundation model doesn't support them. As you can see, Neon Helper, which is used for the ARMv8 Neon code, has jumped up. This is because for the ARC64 implementation, we reused quite a lot of the ARMv7 code and just added 128-bit extensions for the ARMv8. So as a result, we've got a lot more testing there. And as you go lower down the list, you start hitting stuff that's not actually used for ARMv8. So if we take a conservative estimate, we're probably hitting about 70% code coverage of the ARMv8 relevant code. So I reckon on the metrics I put up earlier, maybe between 3 and 48 bugs slipped through our testing. So let's just have a look at how we actually did. Now, I wish I could say that when we delivered ARC64, it was a totally bug-free experience. Unfortunately, there were some bugs. I did the same analysis as I did before on the ARMv7 code, looking for fix. I found about 5 ARM64 specific bugs since we did the 2.0 release. 2 of those, however, were for system emulation stuff. So let's just look at some of them. This is a signed extract narrowing. This was found by some people testing on libav. It's quite heavily used by multimedia stuff. It turns out I would have detected this, but I had a bug in my test pattern. So I'd tested a whole bunch of invalid operations, but I hadn't actually tested the reserved cases. So that kind of underlines the point that even though you might have the test, you probably want to do some coverage analysis to make sure that your tests are hitting what you think they're hitting. Another one was some dead code removal. So this was code that was never going to get executed, so it was never exercised by the Risu tester. But we had all the test patterns for this for the instructions affected, so certainly once we took this dead code out, we reran our test to make sure that we hadn't actually inadvertently broken anything. Finally, we've got the break instruction and TLB instruction, which are bugs that Risu can't deal with. I've mentioned continuous integration, so let's just briefly talk about the challenges for that. One of the problems with potential problems with the Risu architecture is it needs to run on 2 processes. So while this is technically supported by a lot of the various continuous integration setups, it can introduce brittleness because you have to make sure that both a master and apprentice have come up. And one thing that tends to break continuous integration setups is not having your tests very reliable. Unfortunately, the architecture of Risu is fairly simple. It's passive, so the apprentice is just sending data to the master and being told whether or not it's working or not. And you can actually replace that with a straightforward file stream. So we just replaced all the network communication stuff with the ability to stream register compares and memory compares to disk. Obviously, this generates quite large trace files, but fortunately, all the data is pretty much identical, so if you just pipe it through libz, problem solved. Right, let's talk about what we learned from this experience. So, testing is key. The systematic testing we did on Risu was key to our successful delivery of the ARC64 work. The code's been pretty quickly adopted within Linaro, and although we get some complaints, we haven't had many. So it's a pretty good indication of the quality of the final release. I've mentioned coverage analysis briefly. It's important if you want to know how good your testing is. Some people do take this to extremes. I mean, there's areas of the code that we are never going to test, or the GSRT not reached in the translator. It would be pointless trying to test that. But it's useful to know that are your tests testing widely, or are they just testing the same instructions over and over again? So finally, some recommendations. If you're writing a new instruction front end, should you use Risu? Yes. I think the time that you save by doing all your testing up front and planning how you're going to systematically test the instruction will save you invaluable amounts of time, immeasurable amounts of time, compared to just implementing it and committing it and fixing the bugs afterwards. Mature instruction sets could probably benefit as well. They probably won't benefit so much from a systematic approach, but Risu is a useful tool when you're debugging. So certainly if you've identified some instructions that look problematic, then you can just build up some patterns for that particular instruction and really exercise the translator. And of course, building up a library of tests means that you've got some regression testing, so when you do your fancy optimization, you know that you've not broken anything. I've talked briefly about continuous integration. I'll just go on a slight tangent for QEMU's CI efforts. So the QEMU project is a fairly decentralized approach to continuous integration. Until recently, the main publicly visible CI activity was a build-bot instance, which basically attempted to ensure the build still worked on a wide variety of build hosts. I suspect, though, not a lot of people follow the state of that. More recently, we introduced a Travis-powered CI loop. So this attempts to shorten the feedback loop by reporting build regressions straight to the QEMU IRC channel. Although, until recently, it has been a little noisy with a combination of Travis hangs and non-deterministic check failures. Hopefully this is less of a problem now, but it does underline the importance of any CI effort in having reliable tests. Sadly, Travis only exercises a single build host, so we need both Travis and BuildBot to ensure good build coverage. Also, while QEMU has a make check target, which does a fairly good job of testing the common infrastructure in QEMU, it doesn't really address system testing. So there are architecture-specific tests in the test directory, but they mainly have to be manually cross-compiled and then run, well, usually by the maintainers. So Linaro is committed to improving the situation for ARM at least, and we want to expand the range of automated testing we do for KVM and QEMU on our Lava platform. But if anyone else is interested in improving the coverage and situation in QEMU, please do talk to me afterwards. And it's gone and frozen. Ah, there we go. This is not my laptop, so. Right, future work for Risu. So the record and playback code for ARM is still in its own private branch. That still needs to be upstreamed. We've got it working, it works well for us, and the upstreaming tasks tend to slide to the bottom of the priority list. It might be nice to look at improving support for the instructions that have to modify the stat pointer and program counter. Though the philosophy of Risu is not to get too hung up about the things that are complex, because you get quite a lot from just doing all the simple cases. And it would also be nice to see a non-ARM architecture port of Risu, because we're fairly confident that it will help find errors in other instruction sets. Patches are, of course, always welcome. And with that, are there any questions?
So does it make sense to run it inside the system emulator just to see if it finds more bugs?
In the case that I did these coverage slides, I was running the system emulator mainly because it's easier to do code coverage from within system emulation than from within a multiply thought Linux user emulation. But for actual testing, we were doing it within Linux user just because it was a bit faster to spin up. But yeah, run it in as many as you like. The binary itself is statically compiled, so it's very easy to put on whatever you want.
So did you say it doesn't test system instructions?
No, it's, at the moment it's all in user space, so it doesn't attempt to test any system instructions.
Right, is that something that's on your to-do list, or?
It's,
I guess that could benefit QEM, right? If there's something that's going to cause traps in the kernel and, hearing correctness of, I don't know, is that in the realm of what you guys are looking at? Or?
it's a complex problem to solve, because as soon as you start dealing with system instructions, you're talking about a whole bunch of additional state that you're going to have to check that it's done the right thing for, and also check that it doesn't just completely freeze the system. So it's probably not within scope for Risu. Now, I don't know whether or not KVM does emulation of user space instructions in the kernel, and maybe there's a case if there's any of those, but
it would be loads and stores for emulated MMIO that would be the ones that would be emulated.
I mean, I can certainly see something. It would be possible to do something, but you're going to have to come up with a mechanism of checking that whatever the emulated device you were talking to, you had some way of checking its state and comparing it with the master state. So it gets a lot more complicated when you start doing that sort of thing. Any more?
Is it in a Git tree somewhere? At Risu?
Oh, yes, sorry, I didn't put them on the slides, but yes, Peter Madel's got his Risu trees on Linaro's Git server, and I can give you pointers.
So can it handle dynamic instruction length, like if you actually implement an x86 decoder to solve them?
So, sorry, I didn't hear that.
If you wanted to test x86,
Yeah. So the generator itself is done. There is no particular word length limit in how long your instruction has to be. And I think there is a prototype of x86 stuff, but
So it supports stuff, so you can do, you can have an instruction. The generator is just a puzzle in order to it bites into the file. So people write out instruction you want to test. There is instruction in that instruction. You don't care whether your instruction is 16.
I suspect the most complex part will be in the signal handler that needs to advance the PC over the faulting instruction, although I suppose you can make your faulting instructions a fixed width, because it should only be fault. Well, actually, no. Okay. So there are the Risu operations which you can make a fixed width, and you know how to step onto the next one. If you're simulating invalid encodings of multi-length instructions, then your advanced PC coder is going to be a bit smarter than add4.
you could just do a UD instruction and then all in it, just define the word instruction and then still do +4 and keep the other 3 bytes as metadata.
Yeah. My focus isn't massively on x86, it has to be said. Right, any more questions? All right, well, thank you very much.